Welcome to the WISE normal distribution and more. The normal distribution is the most important distribution in much of statistics, but why is that? One might think that it's because many distributions are normal in shape and that this describes a lot of distributions, but in fact that's not true. Very few distributions of things that we measure are really normal. Uh, in this in this video, we'll look at what is the normal distribution, why is it so important, how do we use it, and then we'll look at some fun and important facts, things you can use to impress your friends. Normal distributions or curves can vary in mean or variance, but still be normal in shape. All of these figures are normal curves that differ only in scaling, stretching one axis or the other. If a population is normally distributed, we can use this knowledge to compute probabilities of finding scores in any particular range of interest. The population mean is indicated by the Greek letter mu, and the standard deviation is indicated by the Greek letter sigma. A z-score indicates the number of standard deviations that a score is above or below the mean. Most scores are within one standard deviation of the mean. So for example, here we find that 68.3% of the distribution is within one standard deviation of the mean, just over 2/3. Similarly, about 95% are within two standard deviations, and virtually all of the scores are within three standard deviations. There are tables and computer programs that can help us find these values, and we'll look at some of those in a minute. Now we can use this knowledge to address practical questions. So for example, suppose we have a normal distribution with a mean of 500 and a standard deviation of 100, and we'd like to know what portion of these scores fall between 400 and 600. We can see that most of the scores are in that range, but exactly what percent? The solution is to convert to z-scores, where again the z represents how many standard deviation scores are from the mean. Here, for example, the 600 is one standard deviation above the mean, so it has a z-score of 1. We could compute the exact z-score corresponding to any x-score with this nice formula. Take the x, subtract the mean, and we have the deviation then of the x-score from the mean, divide by the standard deviation to find the number of standard deviations. So here we see again the 600 minus the mean of 500, the deviation is 100, which is one standard deviation, which is then a z-score of 1. Now we can find the probability of finding a z-score between 1 and -1, which is equivalent then to having an x-score between 400 and 600. Well, what is that probability? We can go to our standardized normal distribution and look at what percent of the scores fall between one standard deviation above the mean and one standard deviation below the mean, and it's about 68%. So the answer to our question then would be about 68% of the scores we would expect to fall between 400 and 600. Now let's take a look at some computer programs to help us calculate those numbers. On the WISE website we have the P to Z converter. This nifty little application can be used to find p-values in, for example, in a tail. If we wanted to know the p-value of getting a z-score above 2, it's about 2.3%. We can also enter the numbers directly. So in the example we had here, we were interested in a z-score of 1. Now the z-score of 1 has about 16% off in one tail. It has then double that, about 32% in the two tails, but the area in the middle is 68.3%. On the WISE site, you can find an Excel workbook called StatWise, which has in it many of the basic distributions, including the z distribution. In the window for z, you can enter either the z-value or a p-value, and if you enter the z-value, you will find the p-value associated with it. In this case, for a two-tailed test, the p is 0.317, and so then the area in the inside between the tails is 1 minus that, or 0.683, as we saw before. Another option is to use tables, which you can find in the back of most any introductory statistics book. The distinction between continuous and discrete distributions can be very important. The normal distribution is a smooth, continuous distribution. So consider this example where we have a nice normal distribution with a mean of 500, standard deviation of 100. Question: how likely is it to find a score of 500 exactly on a normal distribution? We might convert to a z-score. Then the question is, what's the probability that z is equal to 0.0000 at set? Well, obviously it's vanishingly small. The probability of any exact value on a continuous distribution approaches zero. Well, so then how can we use a normal distribution to find probabilities? Well, for a discrete distribution, there is a real probability associated with a particular value. For example, if we had SAT scores are distributed in intervals of 10. You may have an SAT score of 490 or 500 or 510, but not 502. To estimate the probability of a score of 500, we could approximate this by finding the area between the real limits of that interval on the normal distribution, and that would be 495 and 505. So we would be looking for a discrete interval on this continuous distribution. Now, what would be the z-scores associated with that? Well, we can use our little formula and find how many standard deviations is 505 above 500. Well, 505 minus 500 is 5. 5 divided by 100 is 0.05. So we're looking for a z-score of 0.05. We could find this by going to a P to Z converter, and if we enter a z-score of 0.05, we find the p-value in the tails of 0.96, which means the probability of getting a score in that interval is about 4%. So the conclusion is that there's about a 4% probability that someone would have a score of exactly 500 on the SAT distribution if we had a nice normal distribution like that. Now, what if the distribution isn't normal? Would it help to convert to a z-score? Well, if we convert from the x-score to a z-score, we now will have a distribution with a mean of 0, and the standard deviation of the z-score is 1. But how about the shape? Well, suppose we had a distribution like this where it doesn't look too bad for normal, but there's a big bump of scores down here at 0. If we convert to z-scores, will we have a normal distribution? Well, each of the x-scores in this bump will convert to the same identical z-score, and we'll have a bump of z-scores. So in fact, converting to z-scores does not change the shape. A critically important point to keep in mind is the normal distribution can be used to find probability only if the distribution is normal in shape. Well, how can we assess whether a distribution is close to normal? There are two common measures of shape: skew and kurtosis. Skew is a measure of symmetry. It's equal to 0 for a symmetric distribution like the normal distribution. However, for a distribution with a longer tail to the right, the skew is positive, and for a distribution with a longer tail to the left, the skew is negative. Sometimes people refer to these as right-tailed or left-tailed distributions. One characteristic of a positively skewed distribution is that the relative values of the median and the mean are predictable because the mean is more influenced by the extreme scores. So the mean is closer to the tail, and that's also true for a negatively skewed distribution. The mean is closer to the tail, whereas in the normal distribution, the mean and the median are both right in the middle. It's helpful to see how the skew is actually calculated. Here's the formula. The important part of this formula is in the numerator, which you see is actually just a deviation score, the difference between the score and the mean, cubed. So a score that's above the mean will have a positive deviation, and a score that's below the mean will have a negative deviation. Now, when we cube a negative number, we get a very large negative number. When we cube a positive number, we get a very large positive number. So we can see if there are very large numbers in either a positive or a negative direction, skew will be pulled in that direction. The standard error for skew has an elegant formula. It's just the square root of 6 divided by the sample size. Now we can test the null hypothesis that the skew is 0 by dividing our observed skew value from a sample distribution by the standard error. And that ratio is distributed according to the normal z distribution, a standardized normal z distribution. That test, however, is not as useful as one might think, and the reason is, as the samples become larger, the standard error for skew becomes very small, and so the tests of significance for departures from normality become very sensitive with really large samples, but they're not very sensitive for smaller samples. And with many statistical applications, as we saw from the central limit theorem, with larger samples, the sampling distribution approaches normal. So in fact, small violations from normality are less problematic with large samples than they are with small samples, and yet the test for significance is most sensitive for the large samples. So the test is sensitive just when we don't need it. Kurtosis is especially sensitive to outliers. It's calculated to be 0 for a normal distribution. Kurtosis is positive for distributions that have a longer than normal tail. For example, here we have a distribution where most scores are clustered near the middle, but there are tails that stick out on both sides. So relative to the tight cluster in the middle, it has long tails. In contrast, a distribution that's relatively flat and drops off quickly at the end has relatively short tails, and the kurtosis is negative. Sometimes people call these short tail or long tail distributions. Sometimes people talk about this, the positive kurtosis, as being a pointy distribution, but I think that's a little misleading because the real action is in the tails, not in the point. The formula helps us see that. The formula for kurtosis includes a deviation score again in the numerator, but this time raised to the 4th power. This means if you have a large deviation in either direction, raising it to the 4th power gives you a very large number, and so kurtosis becomes larger positive when you have extreme scores in either tail. On the other hand, if you have shorter tails than a normal distribution, because of this calculation, you'll get a negative score with the kurtosis. In general, positive kurtosis can be problematic because it indicates outliers which lead to instability in your results. Negative kurtosis is less problematic because we don't have outliers typically. The standard error for kurtosis is also a very nice, elegant formula. It's square root of 24 over n, and it has the same issues as we have with skew. The test becomes very sensitive when we have a large sample. But you can test the null hypothesis that the kurtosis is 0 by taking the calculated kurtosis value for a sample divided by its standard error, and that ratio is distributed according to the standardized z distribution. For many statistical applications, it's desirable to have distributions that are normal or very close to normal. In some cases, a reasonable approach is to transform the raw data to create measures that are distributed closer to normal. A variable like family income typically has positive skew. In the example shown here, the skew is 3.8 and the kurtosis is 20. A rule of thumb is if the skew is greater than 1 in either direction, positive 1 or smaller than negative 1, or if the kurtosis is larger than a positive 1, that's cause for attention to the distribution to see if something might be done to deal with the problem. Now, a distribution with a smooth positive skew might respond well to a log transformation. In this example, if we take the natural log of the distribution of income, we get a distribution that is much closer to normal. And in fact, the skew and the kurtosis are both much closer to 0. In SPSS, the syntax to accomplish this is a compute statement. Compute new variable equal the log of the old variable. Now, if the goal is to compare two groups on income using a t-test, the original measure in dollars would not satisfy the t-test assumption that the distributions are reasonably normal. The result of such a test would be questionable. A t-test comparing groups on the log income would be on much sounder footing. When we take a log, large numbers are reduced much more than smaller numbers. This compresses the differences between large numbers more than the difference between smaller numbers. And one could argue that the log scale on income is more meaningful in terms of behavior because the difference in income of, say, 10,000 and 11,000 is much more important for a family than is the difference between 110 and 111,000. But even the log of family income is not distributed close enough to normal that we would be confident in using a z-distribution to estimate probabilities. In fact, it's rare that any real distribution is normally distributed. So why is a normal distribution so important in statistics if real data are rarely distributed normally? A very important distribution that we never actually see is distributed close to normal, and that is the sampling distribution of the mean. Consider a situation where we have a population that's very far from normal. This is a flat distribution, a rectangular distribution, a uniform distribution, where the scores are distributed evenly from 0 to 1. But if we were to draw 25 scores randomly from this distribution and find the mean, that mean would come from an underlying distribution which is in fact close to normal. This is a distribution of possible means for samples with size 25. From the central limit theorem, we know that sampling distribution of the mean approaches normal in shape as the sample size increases, and that's true regardless of the population shape. So in this case, even with a rectangular distribution, we get a sampling distribution that's already quite close to normal, and then we're able to apply the normal statistics to distributions of means. Okay, now the farther the population distribution is from normal, the larger the sample would need to be for the sampling distribution to be close enough to normal that we can use the normal distribution to find probabilities. A key point is that with careful planning, the sampling distribution of the mean can be close enough to normal that we're able to compute probabilities from the normal or related distributions with a great deal of accuracy. Now we're familiar with the normal distribution, but how in fact is it defined exactly, and how is it discovered? The normal distribution is a mathematical function where the height of the curve is a function of the value on the horizontal axis. But what is that function? And here is the formula. At first glance it looks pretty intimidating, but we can pick it apart and it's really very elegant. The main working part of it is in this exponent on E. It is again a deviation score squared, and the larger that this deviation becomes because of the negative exponent, the smaller the whole term becomes. It has its maximum value when x is equal to the mean and this part is equal to 0, in which case the height of the curve then is 1 over the standard deviation divided by the square root of 2 pi. Now it's interesting, this formula has in it three irrational numbers, sort of basic fundamental mathematical numbers. E is the base of the natural log system. Pi is the ratio of the circumference of a circle to its diameter, and of course the square root of 2 is the square root of 2. The formula can be simplified by converting to z-scores. In this case, the formula is really very elegant. When z is equal to 0, the height of the curve becomes just 1 over the square root of 2 pi, which is just a little less than 0.4, as we see in this figure. Incidentally, the term normal has the technical meaning of perpendicular or independent. For samples drawn from a normal distribution, the sample means and the sample variances are uncorrelated or independent or normal, and that's the source of the word normal. Normal does not have the common meaning of usual. Now, how was the normal curve derived? Well, back in the early 1600s, Galileo noticed that errors in astronomical observations formed a symmetric distribution. In the early 1700s, a mathematician, De Moivre, described the limit of the binomial distribution as a sample increases, and this is a normal distribution. He did his work to understand the probability for gamblers. So like today, often technology is driven by gaming. In 1778, Laplace developed the central limit theorem, and he described the distribution of means as the sample increases, and this distribution is a normal distribution. In 1809, Gauss derived the normal distribution, the full formula for it, to fit random errors, and as a result, the normal distribution is often referred to as Gaussian in much of the world, except in France where it's referred to as Laplacian. And then in the mid-1800s, Quetelet noted that human characteristics were often distributed close to normal. Here are some fun facts about the normal distribution. The curve never touches the x-axis, even as we go out farther and farther to the right. However, that fact may be misleading. There's an interesting characteristic of a normal distribution related to its slope. If we start at the top of the distribution where the slope is 0, horizontal, we move to the right, it gets steeper, going down faster and faster until at some point the slope decreases again and it flattens out. The place where the slope changes from going down faster to flattening out is called the point of inflection, and that point of inflection is exactly at 1 standard deviation. So if you draw a normal curve and you'd like to put in 1 standard deviation, if you can spot where the point of inflection is, that's where the first standard deviation is. Here's an interesting question. If you have a normal curve drawn to scale and at 6 standard deviations it's exactly 1 millimeter above the x-axis, how high is it at the mean? Now you might win some bets with this one. It's over 65 kilometers. That's more than 40 miles. Even more amazing perhaps is this one. If it's 1 millimeter above the axis at 10 standard deviations, how high is it at the mean? And the answer is more than 30 million astronomical units, which is a distance from the Earth to the Sun. So if you ever observe a z-score of 10, you know it didn't come from a normal distribution. Even a z-score of 6 is extremely unlikely. There's only less than 1 chance in 10 billion that you would observe a score that large if you had a true normal distribution. Virtually all of the scores are within 3 standard deviation of the mean, all but about 0.3%. Well, I hope you've enjoyed this little excursion through the normal distribution. On behalf of the WISE team, I'd like to invite you to explore and use the resources on the WISE site, especially the sampling distribution of the mean and the central limit theorem, which might be next in the series for you. And I thank you for your interest and attention.